Good morning, everyone. Welcome to this lecture. Sorry I missed on Monday, I had some issues. I do have issues today as well, actually, but we will study. Maybe if I need a break, I'll ask you, but yeah, we should be able to take our normal one break after the hour. Also, I've come in late because, well, this is technically a 1 hour thing, so but we'll do both hours. Now, hopefully you can hear me. We've been doing MSI logic circuits. We've looked at a number of them. We've looked at decoders. We've looked at encoders. We've looked at multiplexers. We've looked at, I think, yeah, we've looked at those. We are going to look at demultiplexing because we finished multiplexing. Now we are going to look at demultiplexing, and we go on to some other things. Basically, when you're multiplexing, as we saw, you have a number of inputs and you want one output. So that means that a multiplexer has several inputs. It chooses one input to actually move to the output. As I told you last time, it's something we use when we are sharing the channel. How we choose the input to pass through to the output is using select inputs. And these select inputs, the number of select inputs depend on how many inputs you have going into the multiplexer. So for instance, if you have just 2 inputs and you are choosing between one of 2, you just use 1 bit of the select inputs. If you have 4, you use 2, because now 2 bits can give you 4 unique combinations. Now today we want to look at the demultiplexer, and obviously we multiplex. Clearly, if we demultiplex, we are doing the opposite operation. So for a multiplexer, which is here, we have many inputs, we get 1 output. For a demultiplexer, we do the opposite. We have just 1 input, and we pass that to several outputs. Once again, we use select input to choose which output to pass the signal to. So imagine that I want to pass a signal to 8 of you in class. If I use a demultiplexer, my signal is coming into the demultiplexer, and depending on the select inputs, the demultiplexer can choose which of the 8 people to send it to. It will not send it to all the 8 people. It will only send it to the person that is selected by that, the combination of select inputs that are available. Okay, now once again, the reason why this is like a bar is because this is not one bit, it could be a word rather than a bit. So you could have a number of words here. You could have a number of inputs going in here, but you know, all of those inputs, whatever they are, however they look like, will be passed through to just one of those outputs. Now, we have a 1 line to 8 line demultiplexer, okay? We always have a 1 line on the input anyway, and on the output, sorry, and on the output, we can have a number of outputs, but we only send the signal to one of those. We can have 8, we can have 4, we can have 16, and so on. But this is the common one, 1 line to 8 line demultiplexer. And so you can see that we have a signal coming in. That signal goes through every AND gate. That signal or the input is I. It goes into every AND gate. That means that depending on this, on the combination of S2, S1, S0, only one of these AND gates will be enabled. And if it is enabled, then that means that the signal I can go through that AND gate, or the others will be disabled. So for instance, if we look at this being 0, 0, 0, you can see that you have I going through all the AND gates. Then we are going to have our output here as I, and 0 inverse, 1 and 1 and 1, which is I going through that. If our S2, S1, S0 was equivalent to 1, 0, 1, that should be 6, which is this 5, okay? So this is going to be selected, and you can see that you have I, S2 is 1, S1 is 0, so S1 inverse is 1, and 1, which is, once again, I. And so based on these select inputs, the output I will go through a certain output line. Now this table could be drawn as S2, S1, S0, and maybe active, you could say active line, you know. So in future, I'm happy with you drawing smaller truth tables. You could have 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on. And so I would have output 0, output 1, output 2, and so on, okay? So that I know which output has been selected by the given select inputs. Let us look at this. This is something we looked at as a decoder, but we can also use it as a demultiplexer. I think you remember this 74 LS138. It had an enable input, sorry, an enable circuit that had an AND gate and 2 active low inputs and 1 active high input. I think this was, we called this E3. This must have been E2 and E1. In other words, for this to be activated, E1 and E2 should be 0 and E3 should be equal to 1. Now, if when we want to use this as a demultiplexer, clearly you use E1 as your data input. Here you can also use E2 actually, but then you connect E2 and E3, you put them in their active state. So you can see that E3 is connected to a high because it is active high, and that is connected to ground because it is active low. And then you have your data going through E1. Now you have your select inputs, as you can see here. So you can have A2, A1, A0, and your output. That output could have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and so on. And the output that is activated here clearly is going to be O0. That will be O1, O2, and O3, and so on. But what does that really mean? It means that the signal that is here is the one that is going through to those outputs. If, for instance, we took the one of A0, A1, it is A2, A1, A0 being equal to 0, 0, 0, it means that when I is equal to 0, obviously the output, as we have already seen, is the 0. This is the output that is selected. Now, when I is equal to 0, that means that this thing is enabled. That means that output or not will be equal to 0. Remember, these outputs are actually active low. Okay, so that means that the active output state is a 0. Okay, so if our I is 0, that means that E1 is 0. This thing is enabled. It will give a 0 here. The rest will be 1, 1, 1, 1. When I is 1, E1 is 0. If I is 1, that means E1 is equal to 1. Then that is disabled. And when it is disabled, all of these will generate a 1. That means that all of those outputs will give a 1. That means that your output or not is actually 1. That means that for this, I could say signal I is passed to the output. Now, if you have a scenario where you have selected A2, A1, and A0 to be 0, 0, 1, this is going to be obviously the one that is selected, meaning that the signal I will be passed to the output, but this time output O1, I think it is O1. If you had selected that one, the signal I will be passed to output O3. So we can see that whatever we have at the signal input, which is actually going through the first enable input of that decoder, will be passed through to the output, but it also depends on which particular output has been selected. Now, if we look here, let's imagine that I is changing like this, in line with what we have just said. If we are looking at A2, A1, A0 being equal to 0, 0, 0, it means that that signal, however it looks, is passed to the 0 output. And what happens to this one? This is always logic 1. Because these are not selected, so they are in their inactive state. And because these are active low outputs, the inactive state is high, and they will always be high. Okay, so I hope that is quite clear. We are going. Yeah, so excuse me. But before we move on, we can clearly see that we can use a 74 ALS 138 decoder as a demultiplexer, because we can have our input and we pass it through to any of those outputs depending on our select inputs. Let us look at some applications. We have this system, which is a security monitoring system. Actually, before we do this, let's assume that you have, let's for example look at SEDAT, right? There is a question, I think. The enable bit, Yes, when we choose an output using select code, because if this select code is say 111, we are selecting that one. That means it is the one that we have selected, and so whatever is going through here will actually come to this one. Now, if the enable bit is, you mean this part, you can see that this is an AND gate. This is something we studied. So I say that this thing is inside the IC. Of course, you don't see it on the outside the way it's shown here, but you can see that it is an AND gate, and what is coming out of here, we need it to be high so that we can enable. Okay, and how do we get a high output out of that AND gate? We need a low E1, a low E2, and a high E3. And so what they've done here is to connect this permanently to 0 and connect this permanently to 1, which is good. And then this I will either enable the circuit if it is 0, but it will disable the circuit if it is 1. Or the same, when it is 0, whatever output will be selected, that means it is enabled. Because when it's 0, we have enabled. That means that whatever output was selected will generate a 0. A 0 because this is active low. So if you have selected an output, the 0 is the one that makes it active. All of the other outputs will be 1. And if you have selected E1 to be 1, if for instance they say input here is 1, 1 will disable this whole thing, meaning that all of the inputs will actually return a 1. Let us look at a scenario instead that you have many, maybe I shouldn't draw this like that. Okay, so you have several rooms, okay? You have several rooms in Sedat. Let us say that these are our rooms. We have a door here, a door here, a door here, and a door here. And we want to know the status of these doors. A door could be closed, or it could be open. Now, when it's closed, that's good usually, because that's security. When it is open, that's bad. So how could we do this and show it on a panel that certain doors are closed or certain doors are open? So that if they are open, then you can take action. You could use your, that means you need for each of these, you need a line running to the panel, okay? But at the panel, you may need to have an LED that is connected to 5 volts. And obviously this is going to be the same case here and here and here, okay? You could do it like this. But what does this mean? It means that if it is open, return 0. The reason is when you return 0, current will flow through this and you will have light. But if it is closed, you should return a 1 so that you know you have a high here and a high here, meaning that there is really no potential flowing across the LED and there won't be a light. That's how you know that this door is open or closed. Before we leave this explanation, let us look at how you might connect this. You could say that when it's open, you return a 0. So you could have 5 volts somewhere here, and you have that, and maybe you have, yes, you can have this. And then you say that this is open. This is the scenario of open, meaning that you have your LED here and you have another 5 volts. So when it is open, you can see that this is connected to the ground, and so current will flow through that and you can have that LED lighting. But if it is closed, this is actually, oh, okay. So I think I've made a small mistake. Let us see. I think it is, the switch is here. And it can go there. If it is closed here, you know, close, and then you have 5 and 5. If it is open, that means you are here, and close, you are here, that goes to 0, that means you have your end. Something like this. Now the problem with this is that every door would need its own line running to the panel, to the control room or wherever you are having these lights. The other thing, so you have these lines and perhaps they are very long and so on. And so it is possible to find another way to do this. And this is what the demultiplexers can help you with. Actually, we combine a multiplexer here and a demultiplexer here. Let us see how this works. Let us look at, for example, door 0, because all the other doors will look pretty much the same. Now, if it is open, this is open, this is closed. If it is open, what happens? We can see when it is open, this is that. We can see that I naught is equal to 1. Because if it is open, I naught is connected to that, since this is just an open circuit. So really the signal going in there is 1. That means the Z out of the multiplexer is 0. You can see that that is Z inverse. Z inverse. You know, this multiplexer 151 gives us the normal output and its inverse. You know, you should go back and see if you are confused by that. Now, this 0 goes into here. We can see that these 2 and 3, actually this is our 138 demultiplexer, or what we call the decoder. You can see that E3 is 1, E2 is 0, okay, permanently. And so here E1 would also be 0. If it is 0, it depends. You can see here we have a counter. This counter will count from 000, okay, to 111, because we have 8 doors here. Okay, so you can see door 0, door 1, door 3, up to door 7. So those are 8 doors. If we had 16 doors, we would need a 4-bit counter, or a counter, that a mod 16 counter, so that we are able to go through all of the doors. Anyway, let us, for instance, say that in this case, S1, no, S2, S1, S0 is equal to 000. If it is 000, it means that this output has been, sorry, this input has been selected to pass, excuse me, to the output. Equally, this is working in the same way. You can see that what is at S2, S1, and S0 is similar to what is at A2, A1, A0. That means that also A2, A1, A0 will be 000 in that moment. The moment when the max is looking at 000 is also the time that the demultiplexer is also looking at 000. Anyway, so let's continue. We have seen that Z inverse will be 0 because the signal going in here is a 1, it comes here as a 0, and because it is a 0, this is enabled, and because it is enabled, the selected, because we are at 000, the selected input output, sorry, is that. Now, because of this, and you can see that output is active low, that means that it will produce a 0. It produces a 0 because this demultiplexer has been enabled. So it produces a 0, and because there is a higher potential behind this LED, you're going to have light. That is for the case when this is open. You're going to have light because the output is 0. What if the case for closed, for this same scenario, if it is closed, that means that this one is back here and you have this connected to ground. If it is connected to ground, you can see that I0 is equal to 0, meaning that Z inverse is equal to 1. When Z inverse enters this E1 is equal to 1, it disables the multiplexer. Sorry, the demultiplexer. It will disable the demultiplexer. What does that mean? It means that all the outputs of the demultiplexer will return active low, sorry, not active low. They will return their inactive state. And because they are all active low, their inactive states are high. That means in this case, therefore, because we are still looking at S2, S1, S0 as 000, and so also A2, A1, A0, it means we are still looking at this input. In that case, output 0 will actually be 1. And because it is 1, 1 is like 5 volts, there is not enough potential difference here to light, to make that LED go light up. So you can see that depending on the status of the door, you can, if it is open, you're going to have the LED lighting up. If it is closed, you're going to have the LED not lighting up because it is closed. Now, if you are at a panel, you will see the LED for a certain door lighting up, and that will tell you that that door is open. The counter will count through from 000 to 111, and it will loop back to 111, and it will continue looping back. That means for these, as it loops through, it keeps selecting a different door. So this door is selected for 000. Door 1 is selected for 001, door 2 for 010, and so on. This one will be selected when the counter states are 111. And now, obviously, when you are selecting, let's say, imagine that door 0 is open. That means you're going to have light. When A2, A1, A0 is equal to S2, S1, S0 is equal to 000, we are going to see the LED lighting, obviously. However, when these states, these select inputs change, because the counter keeps counting, now it goes to 001, 010, you're going to have, that will no longer light, obviously. The door 0, the status for door 0 will no longer be available to you because obviously now they are choosing a different door. However, during the next round, when it is 000, the status of that door will be checked again. And so that can continue like that. If you are on the panel, you will see, let's say that a door is open. If you're looking at the panel on the LEDs, you will see the LEDs blinking, coming on and off. It comes on when that door has been selected. If it is door 0, it comes on when the counter is in the state 000. It will come on again when the counter has gone back to state 000, and so on and so forth. Yes, Livia, this is what I was trying to explain, that if say two doors, let me try and remove this. Okay. Let's imagine that two doors are open, or two doors or whatever. We have S2, S1, S0, which is the same as A2, A1, A0. And this is 000, 001, 010, 011. Now, let us see LEDs. Now, let's say status. Obviously, this is maybe door. This is door 1, door 0, door 1, door 2, door 3. This continues. Now, assume status. We are going to say, what is the status of the door? Let's assume this one is open, this one is closed, this one is closed, this one is open, and the rest are all closed. So we have two cases of closed doors. You are on the panel. When the counter is counting 000, this LED will come on because it is open. Now, when the counter counts to 001, this LED will be off because door 1 is closed. Now, this LED, in this case, the LED 1, the LED, the first LED that corresponds to door 0 will also go off because obviously it is not being selected. It is not being selected to pass its signal to the output. LED 2 off, and LED 3 in this case will be on, and you'll continue with off here until the counter comes back to 00 state, and then your LED for door 0 will come back. And so if you're concentrating, and then of course you go through this, and when the count is this, your LED 2, your LED 3, when the count is this, your LED 3 will also light. So if you're looking at that panel, you will see LED 1, sorry, LED 0, the one for door 0, and LED 3, the one for door 3, you'll see them blinking one after the other as the counter counts through its range of 000 to 111. Hopefully that is clear to you, Sylvia. Okay. is not something that I'll probably bring, but I want you to understand it. You never know. I could bring it. It depends on how excited I will be. So this is synchronous data transfer. It is synchronous is like serial. Okay, so you can transfer data synchronously. And in this synchronous transfer, you transmit, as we are going to see, you transmit the data serially, but the synchronism is that, you have the clocks, so you are shifting information. So let us see how this looks like. This is a D flip-flop, which is at 1, meaning that this D flip-flop, this output flip-flop 1 will be 1 at, when we get the clock. This is JK. We know that the JK will toggle when J is equal to K is equal to 1. But when J is 1 and K is 0, it is set. So flip-flop 2 will be 1. So now let us assume everything is cleared initially. If everything is cleared initially, it means that F2 is equal to 0. This FF2 will be equal to 0. And if FF2 is 0, you can see that 0 goes into the clear and the clear and also that clear. It means that FF1 will also be 0 in that case. That is initially before we get the clock signal. Now, if this is a counter, it counts the word, and this is a bit counter, which counts the bits. Now we have our registers here. This register, you can see the first register has A3, A2, A1, A0. And obviously we know this to be a word, and a word is made of 4 bits. Okay, so this one will count bits. This will count the word. If, for example, we have transmitted A3, A2, A1, and A0 completely, this counter will increase by 1 because that's the first word is gone. But this one will have already changed 4 times because this counts the bits. So it bits this one, bit that, bit that, bit that. But when all these have been transferred, the word counter will count the first bit, the first time, because that's a word completely gone. So anyway, we have our 4 registers, right? These are registers, and each register has been parallel loaded, okay? Because you can see that this is a PISO, parallel in, serial out. So the information goes in parallel, but gets out in serial. Now, if you notice there is this feedback, this information, it means that yes, for example, A0 will be shifted there into the max, but it will also shifted back to go there to replace A3, because A3 will move to A2, A2 to A1, A1 to A0, but A0 also floats back to where A3, at that point, A0 becomes the most significant bit. Anyway, so let's see how this thing works. We can see that we have our parallel data, paralleled into these 4-bit registers, and we have our clock signal. So initially, before the clock signal, let me see, clock, let's see, action. Before everything is cleared, okay, at the first clock signal, what happens? When the first clock signal comes, it clocks this one. Now, K is 0. The reason why K is 0, this is, remember, everything is initially cleared. So even this output, I'm going to explain what TC is. Actually, what TC is that when you start the counter, when you start the minimum, okay, so the starting point of the counter, which is 0, 0, 0, TC becomes 1. Okay, the same as here. It is almost similar to RC naught, but RC naught is 1 when you reach the terminal state of the counter, which is 1, 1, 1. This one is 1 when you reach 0, 0, 0. You get a 1. Anyway, now when we have our first clock signal, this one will count. Okay, you can see that this one comes in, and if it is active high, so it's a PGT, That means that this Q1, Q0 will count to 0, 1. Now, because this one has not yet reached the terminal state, okay, it hasn't reached the starting point, which is 0, 0, because this has to go 0, 1, 1, 0, 1, 1 until 0, 0 again for this to change. So TC remains 0, and if it is 0, then the enable is also 0, and you can see it is active high, meaning that this one does not count. Let me see if I can actually draw a bigger truth table to enable you to perhaps understand better. Right. Okay, so we are going to have the clock. We can see TC of the bit counter and of the word. Okay, so we will look at both of them. We can see Q1, Q0. This is for the bit counter. Q1, Q0 of the word counter. Okay, let's stop there for now. Okay, so we have 0. This is going to be 0 and 0, meaning that that is disabled. This will also be 0 and 0, and that will also be 0 and 0, because everything is cleared. On the first clock signal, the bit one will count. The TC will still be 0, 0. But this one, for the bit, it will count to 0, 1. And if it counts to 0, 1, this one needs the TC signal to be 1 for it to count. So this one will not count. It will stay at 0, 0. And let us see what happens. You can see that we need the transmit signal to be 1. Transmit signal to be 1. If the transmit signal is equal to 1, that means that you can see that this is a clock into the D flip-flop. Remember, initially F1 was 0. Now FF1 will become 1. If it becomes 1, a 1 is a shift enable, meaning that this data will shift. All right. Remember, this S1 and S0, S1, S0 is still 0, 0. That means that this multiplexer will be focused on I0. That is the input that is selected to go to that. Until this case changes to 0, 1, we are going to continue selecting that. So let me say transfer. That means in this case, we are going to transfer A0. Because this is the first one, and we have got our transmit as 1, so that means we transfer A0, but we need to remember that it also floats back and goes to that side. On the second clock signal, our TC is still 0, 0. For the bit, this will count again, and it will go to 1, 0. Now for the word, it's still 0, 0, because it is still disabled since TC is still 0. And now in this case, because we have got a clock, we have still got an enable and we got a clock signal, we are going to transfer A1. 3, our TC is still 0, 0. The bit counter has gone to 1, 1, 0, 0, 0, 1, 1, 0, 1, 1. Our word counter is still 0, 0. And now we are transferring A2. Okay, I hope that, yeah, I hope that I'm getting this one right. And on the fourth one, we have now our bit counter will go to 0, 0. When it goes 0, 0, TC becomes 1, and the TC for the second one for the word is still I think 0. So I think I should have had word and bit, because I think the word is the higher, is the most significant bit. So let us say 0, 1, 0, 0. In this case, we are going to transmit. Now the word is, it is going to count to 0, 1. because now this has been enabled. Since TC is a 0, this has been enabled, meaning that this counter can transfer data, and we transfer A3, okay? And now we are going to go through the same process again to transfer B. We are going to go through the process to transfer C. We are going to transfer B when the word counter has reached 0, 1. We are going to transfer C when the word counter has reached 1, 0, and we transfer D when the word counter has reached 1, 1. There might be a small mistake around here, but you should go to the book and read about this. But generally, I tried to create a truth table to help you understand better. Now, really, the gist of this is that this information is being transferred A3, A2, A1, A0, and that is followed by B3, B2, B1, B0, all the way to D3, D2, D1, D0. This is when the word counter is 0, 0. This is when the word counter is 0, 1, and 1, 0 for C and 1, 1 for D. However, a copy of the information that you have transferred obviously stays in these registers since we are feeding it back. As I said, TC is high when counter state is 0, 0. So when you are counting 0, 0, 0, 1, 1, 0, 1, 1, when you go back to this, TC becomes 1. When you jump to this step, TC goes back to 0. And then when you reach 1, 1 and go back, once again, TC becomes 1. When you reach 0, 1, TC becomes 0 once again, and so on and so forth. Okay, so the idea of TC here is that when this one has gone through 4 counts, this one counts once. And when this one goes through another 4, this one counts another 1, and so on and so forth. So that means that this one will do 0, 0, 0, 1, 1, 0, 1, 1 4 times. Every time this one is at 0, 0, you do that. That means when it's at 0, 0, you are transferring word A. When at 0, 1, you are transferring word B. At 1, 0, you are transferring word C. And at 1, 1, word B. But each of these words requires 4 counts on the bit counter. Okay? Yeah, a little confusing, but when you read the notes, you will understand. This one works pretty much the same way, so I will just jump it. Once again, I don't know how I would ask something like this, but it's necessary that you also understand these things. It's not that I'm teaching you everything so that I'm able to ask you to repeat it. And so, yes, I would encourage you to read it and understand it, because it is possible that I can do a smaller circuit based on this and ask questions about it. Let us go to a magnitude comparator. A magnitude comparator, as you know, the name suggests, you are comparing magnitudes of 2 words. These are your data inputs. You have word A. As you can see, these are 4-bit words. And you have word B. And you are comparing word A and word B. Let's assume that this is 1011 and 111001. Now it has 3 outputs. Output A greater than B, output A less than B, and output A is equal to B. As you can see here, these outputs are active high. So that means that if A is greater than B, then O A greater than B will be 1, the rest will be 0, clearly. If they are the same, then this will be high and this will be low. If B is greater than A, this will be high and this will be low. These are called cascading inputs, and I'm going to talk about them in a moment. But how do you know which word is larger than the other one? We start from the MSB side. And so in this case, you can compare this. You can see that in this position, they are the same. In this, the next position from the most significant bit side here, they are the same. But when you reach here in this position, you can see that A is greater than B. It doesn't matter what the lower positions are, as long as you notice that A is greater than B, that means word A will always be greater than word B. And so your output, A greater than B, will be high. That is how we compare words. If I have 1000 and 0111, I compare this. Even though this side is there zeros and these are ones, this word is always larger than that word. Because in the most significant bit position, that it is a 1 and the other one is a 0. So in fact, this is 7, for instance, and that is 8 if you were to convert into decimal or hexadecimal or whatever. Now, this is a 74HC 85. It can also be a 74 LS 85 for TTL. HC. Now, these cascading inputs are interesting because they enable us to connect several magnitude comparators, excuse me, to compare longer words. For instance, let us assume that instead of, this is clearly a 4-bit comparator, but what if we had 8-bit words? If we had 8-bit words, then we connect one comparator through this one. So these outputs, so we would have now another comparator, and these outputs are like that. This is A equal to B, this is A less than B, and this is A greater than B. So we would connect this one to that, would connect this one to that, and would connect that one to that. I'm going to show you in a moment how that would work out. But before we go to that, let us look at this truth table. So I should mention that when we are comparing just 4-bit words, two 4-bit words, we should connect these low and that one high. That is the right connection. If you want to get the right output or the right comparison, you should connect your inputs, cascading inputs like that. That is in a situation where you're not, where you're only comparing 2-bit words, meaning you just want one comparator circuit or one comparator IC. This is how you connect them. Let us look at this truth table. If A3 is greater than B3, we have already seen that if A3 is greater than B3, then word A is definitely greater than word B. It doesn't matter what B2, B1, B0 are. It's similar to the situation we looked at, which was 1000 and 0111. Obviously, this is A3, A2, A1, A0, and B3, B2, B1, B0. As long as A3 is greater than B3, already the word A is greater than word B. And here, this will be high, that will be low, and that will be low. Now, with these cascading inputs, I've actually been having an issue with them, but I think if you are comparing 4-bit words, then this should be, and this is a 4-bit word, then we have just said that this should be low, low, and high. This is how we should be connecting these ones. Let us look at this case. What if A3 is equal to B3? Then we go to the next one. We compare A2 and B2. A2, if A2 is greater than B2, or A2 is less than B2. If A2 is greater than B2, we don't care what these others are actually. But if A2 is greater than B2, then we are going to have A greater than B as a 1. And I think you can see in this case that A greater than B is a high. But in this case, if A2 is less than B2, then A less than B will be a high. Obviously, this will be low. So when it is active, when it is the right result, the output will be high. And for the others, the output will be low. And so really this is quite easy. Let us look at this case where A3 equals B3, A2 is B2, A1 is B1. But now we see A naught is greater than B naught. If that's the case, then that will be high, the rest will be low. But if A naught is less than B naught, then that means B word, the B word is greater. And so this is the one that gives you high. This would be similar to 1, 0, 0, 0, and 1, 0, 0, 1. This clearly here, B will be greater because we can see that these are similar in all these three positions until the fourth position. Right, let us look at the case I talked about. You can see here that if you have 8-bit words, you put A3 to A naught and B3. You first compare A3 to A naught and B3 to B naught in IC, I could call it IC1. And then you compare A7 to A4 and B7 to B4 in IC2. This being IC2, this being IC1. Now, in fact, when we are comparing these, we can see A7, A6, A5, A4, all the way to A naught. Let me call A2, A1. And this will be B7, B6, B5, B naught, B3, B2, B1, B naught. As we said, a comparison starts from the most significant side. So if you have your connection like this, you can see that this input goes through the cascade. These are the cascade inputs. And that's really what it means. You use them to connect several of these together. And you can see that this connects to a similar input. So that shouldn't confuse you. However, if you are comparing these, you would first look at IC2. Why? Because it is the one with the higher order bits. So you can look at A7, A6, A5, A4, and B7, B6, B5, B4. If this one determines that from these, this first part, IC2 determines that, for instance, B is greater than A, then it will generate a 1 here and a 0 and a 0. But if it determines that A is greater than B, it will generate a 1, a 0, and a 0. It doesn't matter what is on the IC1, because IC1 are lower order bits. Whatever they are, they cannot change the outcome. However, in a situation where B7 to B4 is equivalent to A7 to A4, this IC will now consult IC1. It will see from IC1 which of these is high. If it is, for example, B, then that means that this would be a 1. And if there is a 1 coming in here, then what this one does is that it will make this one once again high, because it is just picking a result from the other stage. If the higher order bits are similar, then you look at the lower order stage, and depending on which one is bigger, that is the one that you highlight at the output. So this is how you can compare. You can compare, say, 8-bit words using 4-bit word comparators. Let us look at an example like this. We have 1, 1, 1, 1. This, I'm looking at this case. This is A3 to A naught, and this is A4, A7. A4, A7 is 1, 0, 1, 0. Now B is going to be, actually it is going to be 1, 0, 1, 1, whereas this is 0, 0, 0, 1. Okay. Now we said we start with IC2, and so you can clearly see that this will determine that B is greater than A. So that means you're going to have a 1 and a 0 and a 0. That is irrespective of what is coming from that side. Okay, but what if What if this was different? So as we can see, in this case, we have our 111 here and 1010. Here B, we have a 1010. No, we don't have a 1010. We are looking at lower order bits, which is 1001. Whereas here we have, I think I'm making a mistake. Let me just repeat this. Yeah, so if we are looking at the same A7 to A0, we have on the higher order bits 1010, and this one will also be 1010. And on the lower order bits, we are looking at 1111, and this one is 1001. In this case, we can see that from here, B is equal to, no, B74 is equal to A74. So this IC2 is unable to determine which of these two is bigger. So it goes to IC1. IC1 will have returned A greater than B, meaning that this is a high. And so it will look at whichever is high, and it will activate that output to be high. So you can see this is how you can know which one is high. So that will be high. The rest will be 0. I want us to have a short break of 5 minutes so that I can catch my breath. Let's have a short break of 5 minutes. I will start immediately at 11:15. I'm back. Let's continue. Richard asks, in the case of high order bits, A and B, which is the most significant? I'm not very certain that I get your question. But usually when we write B as B7, B6, you know, the B naught, these would be more significant. You start this side. And so we start our comparison from that side. And so because these are the ones going in here, B7 is the most significant and A7 is the most significant here. And because we are starting on this side, if we can begin by comparing these higher order bits against each other, if here we can determine which one is larger, we don't need to bother with that one. It's a moot point. We can, depending on, it doesn't matter what these are, as long as one of these is larger than the other, we are going to have our larger value without considering the lower order bits. Okay. Let us look at data busing. Data busing, in computers, we usually transmit information, and this information is transmitted on signal lines that are called buses. Buses, you'll find like a signal line with a thing with like 16 signal lines or 8 signal lines or 4 signal lines. And if you've seen inside a computer, there are these things that they call bus cables, for instance. Those are exactly what we are talking about as buses. Namwanja, we don't know what ends at midday. Now, these are 8. And usually, it is the case that you don't have so many buses going through on the computer. You reuse the same buses. And so you might have so many circuits that use the same buses. It's like having the same road and so many people, so many cars are sharing that road. That's what we do. And so you must figure out a way to share this. This is what is involved within data bus. Now, you can see, for instance, that this microprocessor is receiving information from this bus. Okay. Thank you for alerting me to that. I had moved my mouthpiece away. I'm sure now it's so much better. Yes, so as I was saying, within a computer system, you have these buses, and these buses are shareable. So many pieces of the circuit, or parts of the whole computer circuit, all these different registers, multiplexers, all of them are using these same buses. So they are sharing them. So how do you ensure that they do not send information at the same time on the bus, and then you have a problem with contention, obviously interference. So this is called bus contention. If this one, you can see the microprocessor or the CPU is receiving information from that bus. This counter is sending information to that bus. This counter is sending information. I don't know what is that. DIP switches. They are sending their information to the same bus, and this keyboard is sending its information to the same bus. If all of these were to send information to the bus at the same time, then this information is going to interfere and you will not get anything out of it. So this really brings us to the idea of tri-state outputs. And when we are dealing with buses, we use tri-state outputs and inputs, so to speak. And if we don't use tri-state inputs or outputs, we use tri-state buffers. What do these mean? A buffer obviously is like another piece of equipment. So you have normal outputs, but you add some other piece of electronics that buffers this information. What does this mean? What is tri-state? So previously we've always found that we have 2 states. States 0 and 1. This is, since first year, this is what we've always believed. Actually, there is another state that we have hidden from you up until now, which is called the high Z state. The high Z state is like a disabled state. So it is very difficult to know what state it is. It could be somewhere in the indeterminate range. So you know usually that you have, for example, for TTL, you have 0 volts to 0.8 volts, that is state 0, and 2 volts to 5 volts, that is state 1. Usually there is this indeterminate range, and usually this is where the high Z state is. So you cannot really say that I know the state of Z. It could be high, it could be low, it could be somewhere within there. The idea though of the buffers is that before it is the turn of this counter, for example, to send information to those buses, the information will be held here. And usually when you see an IC with something like that, you know that that IC has tri-state inputs or outputs, and or it has tri-state buffers. Those buffers block the signal from going to the buses before it is its turn. And so this one could, you know, this, if this one, the counter is sending its signal to these ones will deploy their tri-state buffers or tri-state in outputs so that their information does not get on the bus. This is how you share the bus so that each one has access to the bus and does not have to contend with others or interfere with other information from other parts of the circuit. You can see that we have enable 3, enable 2, and enable 1. Okay. Now, if enable 2 is, for instance, 1 going into the buffers, these buffers will be enabled, or you know, it's like opening a gate. The signal can go through to that. That means you cannot have enable 3. You can't have enable 1 equal to enable 2. This is interference. If enable 1 is 0, enable 2 might be 1. Then enable 2 will be able to, you know, this one, this case here, the counter, is that enable 2? No. Enable 2 is the keyboard. That means information being pressed at the keyboard can now go and be sent to the CPU. But if you now want to send the counter information, you need to disable that one, meaning now E2 becomes 0 and E1 becomes 1. We are going to study more about this actually when we start looking at memory. Memory, I said, uses registers, and we have so many registers, and we have information flowing back and forth between the CPU and the memory. So we are going to be seeing how this is done, and you're going to find that we use a lot of high Z states, because we need to use high Z so that some registers are in their high Z states for others to be able to use the few bus cables that are available. Does that mean that we can have an infinite number of circuits using the same bus, or there is a limit? It is an interesting question. I think an infinite number of circuits means that you would need infinite time for all of those circuits to have access, for instance. So maybe what you want to say is, can we have a large number of circuits sharing the same bus? And I think the answer is subjective. There is no clear limit on the number of, for instance, registers that could use the same bus. This could be a very large number. It could be 1 million registers using the same bus. It doesn't matter. Most of your memory now is in terahertz. So you can imagine if each of those registers needed its own line. But most of them will usually use the same bus, because usually when you go into memory, you provide an address. And that address selects one register out of the millions of registers that are within your memory. Now, because usually that address is also the one that enables the buffers. It enables that memory to be able to send information. And if that address, you know, of course, that address is only unique to that register. Now, the right address will enable that register, you know, of that register of which it is the address. All of the others will be disabled. In other words, they are output buffers or their tri-state outputs will be on, meaning that information cannot flow to that line. And usually this is how it is done. And so even if you had 5 million registers, 10 million registers, 100, I don't know, whatever number, you always provide a unique address to just one register. And usually those registers are like 4-bit or 8-bit. And so usually you're looking at generating like a byte. A byte of information is 8 bits. However, that unique address is also the one that enables that register to send information, to put its information on the data bus. And because that address is only unique to that register, all of the others will be disabled by default. Okay, so I think that is a good number, but I wouldn't say infinite, because infinite is nobody knows what infinite is actually. However, you see that I think I should tell you this has nothing to do with digital electronics actually, is that the word infinity does not mean a number that you have never seen or heard of or you cannot calculate. It depends on the context. It depends on what you are measuring, the measurand. So if we are looking at the age of human beings, we know human beings can grow to 100, 120 years and so on. So if I said the age of, I could say the limit, the infinity age when it comes to human beings is like 200. That's enough because nobody can live up to 200. And so that is already infinity in terms of age of people. Infinity usually is a number that is unattainable depending on what measurand you're looking at. So in the case of memory, if I can have 100 million registers, of which each register is like 16 bits or 8 bits, then that's already a huge number, but it is not anywhere close to what is possible when you are looking at this fabrication of, the miniaturization of digital electronics. It means if you are to say 1 billion registers is infinity, you might actually find that that is an unattainable target. Let us look at this other part. Actually, this one is supposed to be there. Sorry about this. This is supposed to be there. We were looking at this and we were comparing. This is the magnitude comparator. And so this is an application of a magnitude comparator, something that I've called threshold testing. Sometimes you want to compare the two values to determine what to do. So you might be monitoring temperature and you know your threshold temperature. Let's say my threshold temperature is 20 degrees. And I say that if the temperature is below 20 degrees, I do something or I don't do anything. But if my temperature goes above 20 degrees, then I should do something. It could be that now if it is below, now here you see we have a furnace controller. That means we have a furnace is a source of heat. So it means that if my temperature vis-a-vis threshold, so maybe this is 22 degrees centigrade. If temperature is below, compare. We are going to compare the current temperature vis-a-vis the threshold temperature. So if like my temperature is 18 degrees centigrade, I should turn on the furnace until my temperature is at least equal to 22 degrees, or usually when you read the book, you realize the way they've said the question needs you the temperature to be greater. And now when the temperature is greater than 22, I can now get a signal to switch off the furnace because I want to keep the temperature, to regulate the temperature around that. So this could be used with some thermostats and so on. Obviously, we are comparing numbers. So any scenario where you're comparing things, and especially in control systems, you can use these magnitude comparators. Let us look at this. This is an OR gate. If you remember, this is an OR gate latch. I put the truth table for you here because I know some of you have forgotten. So here we have control temperature. And so we have a keyboard or a keypad, and you can just type the temperature value that you want. Let's say this is our 22 degrees centigrade, and this 22 is stored here. we make it binary. So depending on whatever binary number it becomes, we have our 22 degrees centigrade stored there. Now here we have a temperature sensor. Okay, so this is maybe the room. We have a temperature sensor that takes that signal into an analog to digital converter. Already this is digital because we have a keypad, encoder, and register. So already we have, but here because the temperature is an analog signal, we need to convert it into a digital signal and store it here. So let us say we have A7 to A0 and B7 to B0. Let us compare and see what happens here. If B is greater than A, what happens? If B is greater than A, this is what happens. Set is 1. That means clear is 0. When set is 1, what happens? The output is 1. Actually, this is, I think the output is somewhere there. You look at this latch again. You can see here, when you have set, the output is there, opposite. So that is going in there. Okay, so if B is greater than A, we need to turn the furnace on. And that is why we have a set output of 1. That sets the furnace on. If B is less than A, we can see that if B is less than A, the output is here. That means A is greater than B. That is a 1. A 1 is going to clear. So if we have a 1 at reset, we clear that. And that really means that we have turned the furnace off. Turn furnace off. If the set signal is less than the current, the set temperature is less than the current temperature, then we want to reduce the temperature to match the one we set. But if the set temperature is greater than the current temperature, then we want to heat up the room to approach the temperature that we set. So you can see how this regulates the temperature. Okay, so this ends our look at MSI logic circuits. There is one or two others I ignored. You can choose to ignore them as well. But this is pretty much it. Just one moment. Marvin, I see that makes the bus serial, and thus it can't do simultaneous registers at a time. Yes, technically, it can't. Well, it is like serial and parallel at the same time, maybe. But usually you have something like this. So memory will be usually arranged in this way. So you have one register, another register, another register, and they are packed like this. And in here you store your bits. So you have your flip-flops in here. Each line is a flip-flop, and so on. Now, usually you give an address. And usually you also give a command of either to read or to write. If you are reading, that should be 1. If you are writing, that should be 0. Also going into that memory. If you are writing, you must provide also the information you want to write. If you are reading, that information will just go to the CPU. Now this address will be unique to one of these. Let's say that you have picked this address. These 8 bits can go on the bus. Okay, so you have buses running here and they will connect through here and so on. And so if you have selected this address, it will enable the buffers here, but it will disable the buffers on all the other registers, all of them. Okay, so that address is the one that enables the buffers, particularly of that unique register that you have transmitted. Now, this information will usually go out in parallel. It will go on the bus, each bit on a specific line, and it will go to wherever it's going. Or if you are writing, you will provide your 8 bits on the bus so that they can be shifted into memory. So it might be series in the sense that you have disabled everything else and you're looking at one register, but it is also parallel in the sense that either you're parallel loading or you're reading the information, but in parallel simultaneously. Okay. I want to, just one moment. I want to talk about something else because we've finished this and I want to introduce something new. Now we were talking earlier about digital and analog. We know that digital either is a 0 or a 1 or tri-state, but for now let us leave the tri-state out. We usually ignore it until we need to use it. Now this can be 0 all the way to 0.8 volts, and this can be 2 all the way to 5 volts. That means if I have 3.67 volts, that is bit 1. If I have 2.10, that is volts, that is bit 1. If I have 0.1, that is bit 0. If I have 0.7, that's bit 0. In other words, with digital systems, the actual value does not matter. What matters is the range. Make sure your value is within the right range. This is why actually that digital systems tend to be a bit robust when it comes to noise and so many other things, which makes them popular. With analog systems, if you have a 0.1 voltage and 0.7 volts, these are completely different values when we are looking at analog systems. 0.1 is not the same as 0.7, but in digital, they are actually the same. So now we are going to look at how to interface the analog world to the digital world, because most of the things that are within the world physical phenomena is actually analog. Time is analog. Temperature is analog. Pressure is analog. Humidity is analog. What else? All of these things. Heat is analog. Radiation is analog. All of these things that we are measuring tend to be analog. And so usually we are looking at a physical phenomena. This can be temperature, humidity, pressure, etc. And we need to create an analog signal. We want to create an analog signal. And an analog signal obviously is an electric signal. So how do we convert pressure into an electric signal? We usually use something we call a transducer. A transducer is a system or like a piece of electronics that converts one form of energy to another. And when we are measuring these things, we are converting whatever that form into electrical so that we can use our electronics to process it. Now, transducers are usually sensors. So you have a pressure sensor, a temperature sensor, soil moisture sensor, humidity sensor, and your thermometer and your thermostat, and so on and so forth. These are sensors. Now, after this, because we want to move this into a digital circuit, we need to perform what we call analog to digital conversion. We need to convert an analog signal into a digital signal so that it can go into a computer or into your microprocessor and so on. The piece of electronics that performs analog to digital conversion is called an analog to digital converter. Analog to digital converter, or ADC, analog to digital converter. Then usually this goes into, I've put a number of lines because it might have been converted into 4 bits and we can move it in parallel. You can also move it in series. This is your CPU or your digital system. Now, usually this now goes into what we call a digital to analog converter, DAC. So for us to make sense out of that information, we need to convert it back into analog. And so we have a DAC, a digital to analog converter, and usually this information now goes into a piece of equipment that we call an actuator. Actuator is that thing that changes the phenomena, the physical phenomena. So you can see, for instance, in the example we just had of the furnace, your furnace now would be the actuator. You don't have good temperature, you have low temperature, you turn on the furnace and it will increase. You have very high temperature, you will switch off the furnace so that the temperature can drop down. That's with temperature. If you're looking at soil moisture, if your soil moisture is low, you can switch on the sprinkler system and your sprinkler system would now sprinkle water and improve the soil moisture. That sprinkler system is your actuator. But if the moisture goes above a threshold, you turn it off and you're back to, so that the soil moisture can reduce. You know, that is the process of actuating, trying to influence the value of the physical phenomena. And so you can see that you start by measuring the phenomena, okay? It is really similar to what we did here. You need to know this temperature, so that's where we are. And you measure the phenomena, the physical phenomena, convert it into digital. And then, of course, first of all, analog, because when you measure it, you use a sensor and the sensor output is analog. Then so analog to digital to a computer. From a computer, you go back to analog to give you analog. And then this usually goes to an actuator. So we are going to continue speaking. Next time, we are going to talk more about these matters. We are going to be looking at digital analog conversion and analog to digital conversion, so that we can, this will be a new chapter. I think it is the third, it will be the fourth last chapter, but one of those four is really small. So it is this one and the memory and PLCs, PLDs, and then we might look at chapter 8 briefly. Okay, so you should have a nice day. Please read. I've given you an assignment, and by the way, before you go, let me just say that for people who don't have groups, it shows a very high level of unseriousness, because I talked about groups, I think, over 3 weeks ago, or maybe 2 weeks ago. And for somebody to say that they have communication problems, to me tells me that they've also not been coming to class. I mean, how are they expected to pass? So if you're not really following the course, you're unlikely to pass, and so I don't have to waste my time reading your work. So I'll not be giving people a chance to create more groups. Hilda, the deadline is not too near. I disagree that the deadline is too near. Do you guys have, I'm sure you have Multism, because I gave you a copy in your first year. I mean, you are 8 people, 7 people, okay. I think 6 or 5 people. That deadline is not too near for 5 people. Usually when I'm doing these things, I'm thinking, okay, how much time does each one have to spend? I don't expect that you people need to meet and do this work. Maybe you need to meet. I don't know how you want to do it. I know that usually it's 1 or 2 people that does the work anyway. But I don't think that the deadline is too near. Maybe John Baptist wants me to add almost 4 days to the deadline. Let me first see, what deadline did I give? Let me just see. You know, I want to be fair. I don't want to be unfair. 7th April, Wednesday. Hey guys, today is Thursday. That's a whole week. Is today Thursday? Today is Wednesday. A whole week to 7th. Okay, I'll give you Friday 9th. But please, that is a hard deadline. If your work doesn't come in, please don't bring it. Friday 9th, by around 2 p.m., make sure that your class rep has your work and they can bring it to my office by 2 p.m. And please don't put it on the class representatives. If they don't bring your work at 2 p.m., don't make it a big deal. For them, their job is to deliver what they've received, and it is your duty to make sure that they receive that work in time, okay? All right, have a nice week and enjoy your Easter. I'll also be putting some ELE exercises for you. It's just that I don't have time at the moment. But please, we are really now trying to ramp up the activities around the course. And so please, you need to start revising if you've not been revising. Okay, great, bye.